Thanks for joining me. My name's Carly Christensen, and today I'll be telling you about ZeroFlux, a company that provides same-game pricing technology to the wagering industry, and how we use ScyllaDB to ensure that our customers have low latency no matter where they are in the world. So if we look at our agenda for the day, first I'll be covering off who ZeroFlux are and the processes that ZeroFlux follows, the challenges that we faced, and how we used ScyllaDB to overcome those challenges. Finally, I'll be covering some of Charybdis, our open source Golang package that we've developed to help us maintain our key spaces. So I've been in the IT industry for about 20 years now, primarily as a software developer. I also spent a few years as a SQL Server consultant at Water IT Solutions. And prior to ZeroFlux, I was the head of trading solutions at Entain Australia, which is a team that processes all of their incoming data feeds. So what is ZeroFlux and what do we do? ZeroFlux primarily provide same-game pricing technology to the wagering industry. We allow customers to price bets on correlated outcomes within the one match, and this allows them to explore their theory of the game. It's much more exciting than just placing Team A to win bets. So if we were to look at a same-game example, we have three markets. The first is the match winner. Will Team A or Team B win? The second is which player will score the first touchdown? And the third is the total score market. Will the combined scores of Team A and B be over or under 45.5 points? If I wanted to place a bet on Team A to win and B Boomer to score the first touchdown, but I thought it would be a low-scoring game, you could have a look at these outcomes and multiply the prices together and get a price of around $28. But in this case, the correct price is actually more like $14.50. And this is because these are correlated outcomes. So we need to use a simulation-based approach to more effectively model the relationships between those outcomes. If Team A wins, it's much more likely that they will score the first touchdown or any other touchdown in that match. So we run simulations, and each simulation models a game end-to-end, play-by-play. And we run tens of thousands of these simulations to ensure that we cover as much as of the probability space as possible. So we have a look at the ZeroFlux process and architecture. Our platform has been designed to be cloud native from the ground up. Our software stack is run on Kubernetes and is hosted in Oracle Cloud Infrastructure. At the moment, we have over 130 microservices, but that's growing every week. And a lot of our environment can be managed through custom resource definitions and operators. For example, if we want to add a new sport, we just define a new instance of that resource type and deploy that YAML file out to all of our clusters. Our services are primarily Golang, and we use Python for our modeling and simulation services. And we use gRPC for the communications between all of those services. We utilize Apache Kafka to ensure at least once delivery of all of our incoming and outgoing updates. And we use GraphQL for our external-facing APIs. So our data flow process starts with receiving content feeds from multiple third-party sources. Those content items can then be combined into booked events, and whenever we receive an update of a content item, we'll trigger a reprocess of that booked event. Once the update is applied, we will start running our simulations again. And when complete, we can use the results of those simulations to generate hundreds to thousands of new markets that are stored back on the original event. Our customers can interact directly with that booked event, or they can use our API to request prices for custom combinations of outcomes via our query engine. And we use our stored results from our simulations to answer those questions. So what have been our main challenges? Our ultimate goal is to be able to process and simulate events fast enough to be able to provide same-game prices for live in-play events. We need to be able to answer questions like, will this corner result in a goal? Will this team score the next? Will this play result in a touchdown? And which player will score the next touchdown? And we need to be able to do this fast enough to provide prices before that play is finished. To do this, we need to optimize for time over any other factor. So we have two main challenges. Our first one is that we have an incredibly high throughput and concurrency requirements. Events can update dozens of times per minute, and each one of those updates triggers tens of thousands of new simulations. Simulation data can be hundreds of megabytes, and at the moment, we're processing about 250,000 in-game events per second. Our second challenge is that customers can be located anywhere in the world. So we need to be able to place our services and our data with them. With each request passing through many microservices, even a small increase in latency between those services and the database can result in a big impact on the total end-to-end processing time. So we looked at a lot of options. We looked at MongoDB, which several of the team had used before, and so we were fairly familiar with it. But we'd found issues where when there were a high number of concurrent queries, some of those small queries could take seconds to be returned. We tried Cassandra, and even though it supported the network-aware replication strategies that we needed, it just didn't have the performance and resource usage that we needed. We also looked at Cosmos DB, and it addressed all of our performance and regional distribution requirements. But as a startup, we just couldn't justify the high cost. And since it was Azure only, it would limit our future portability options. The winner was ScyllaDB. So we had trialed ScyllaDB in a previous project, and even though it didn't work for that situation, we knew that it would be perfect for ZeroFlux requirements. It supported the distributed architecture that we needed, so we could locate our data replicas near our services and our customers to ensure that they always had low latency. It also supported the high throughput and concurrency that we required. We haven't found a situation so far where we can't just scale through. It was also easy to adopt. By using Scylla Operator, we didn't need to have a lot of domain knowledge to get started. So let's look at our architecture with ScyllaDB. We use ScyllaDB open source, and we're hosted on Oracle Cloud using their Flex 4 VMs. These VMs give us the option to change the CPU and memory allocated to those nodes if needed. It's currently performing very well, but with every customer that we add, our throughput does increase. So we're aware that there may come a time in the future where we need to scale up and move ScyllaDB to bare metal instead. In development, we use Scylla Operator, but for production, we've moved to self-managed because Scylla Operator only supports a single Kubernetes cluster, so that made it a bit difficult to scale out geographically. We're also still reviewing our strategies around Scylla monitoring and Scylla Manager. To make the most of Scylla, we have divided our data up into 3 main categories. The first is global data, and this is slow changing data that is used by all of our customers. And so we replicate it to every one of our regions. The second type is regional data, and this is data that is used by multiple customers in a single region. For example, a sports feed. If we find that a customer in another region requires that data, we will separately replicate it into their region. The third type of data is customer data. And this is data that is specific to that customer, like their booked events or their simulation results. Each customer has a home region where we'll keep multiple replicas of their data, and we can also keep additional copies of their data in other regions that we can use for DR purposes. Just to illustrate that idea, let's say we have a customer in London. We will place a copy of our services, which we call a cell, into that region, and all of that customer's interactions will be contained in that region, ensuring that they always have low latency. We'll place multiple replicas of their data in that region, and we'll also place additional replicas of their data in other regions. And this will become important later. Let's say we similarly have a customer in the Newport region. We would place a cell of our services in that region, and all of that customer's interactions would be contained within the Newport region, so they also have low latency. If for some reason the London data center becomes unavailable, we can redirect that customer's requests to the Newport region. And although they would have increased latency on the first hop of those requests, the rest of the processing is still contained within one data center, so it would still be low latency. And that would also prevent a complete outage for that customer. We would then increase the number of replicas of their data in that region to ensure data resiliency again for them. So our data is segregated between services and key spaces. Every service uses at least one key space, and some of them have quite a lot. So services that use global data, or our global data has one key space that's replicated to all of the regions. Our regional data has a key space per region, and our customer data has a key space per customer. So some services may actually have more than one type of data, and in that case, they may have both a global key space as well as customer key spaces. So that brings me to Charybdis, our open source Golang package. And we named this after the other sea monster that often features in Greek mythology alongside Scylla. Our main drivers for developing Charybdis were that we needed a simple way of orchestrating the management of our key spaces between all of our services. And we also found ourselves repeating table operations that were very similar between many of our services. So we created Charybdis, and this provides a table manager, which can be used to create key spaces, create tables, add columns and indexes as required for that service. It also offers simplified functions for CRUD-style operations, and it also supports TTLs and lightweight transactions. So if we look at a simple topology scenario, our service has its tables defined in Golang structs that include data types, column names, and partitioning and indexes. We then can use, here's an example of a simple setup function that can be used to initialize and manage the key spaces for that service. Under the covers, that's actually being converted into DDL statements that are applied to the database. That table manager can then also be used to call the simplified functions for table operations. So here's an example of an insert statement, and all we require is a definition of the data that we want to insert, and we can call manager.insert, and it will all be done for you. In this example, we also have applied a TTL to that record with a very simple additional option. To retrieve that record, we call manager get by primary key, and just include the values of all of the primary keys in order in that request. And finally, to update, we edit the original object and call manager.update. And again, here we've applied an updated TTL for that record. So in our environment, we actually use network-aware topology. So alongside every one of our services, we also have a topology controller service. And this service is responsible for managing the replication settings and key space information related to every service. So on startup, the service will call topology controller and retrieve its replication settings. It will then combine that with its table definitions and use that to maintain its key spaces in Scylla. You can see here is an example of some DDL statements generated by Charybdis that include a network topology strategy. So we still have a lot to learn, and we're really early in our journey. For example, our initial attempt at dynamic key space creation caused some timeouts between our services, especially if it was the first request for that instance of the service. And there are still many ScyllaDB settings that we have yet to explore, so I'm sure that we'll be able to increase our performance and get even more out of ScyllaDB in the future. Thanks very much for your time. If you do have any further questions, you can contact me using the information on this slide. And there's also a link there to our Charybdis Golang package. Thank you.